Can everybody hear me? Yes, that's good. My students, I sometimes teach 300 students, they always complain that I'm too loud. So in that situation, they can't sleep long enough. That's the situation. So my name is Robert Buchwaldt. I'm not in the program. I'm the surprise candidate here. If I see it correctly, I'm born and raised in Germany and came over to the United States for a PhD. I spent some time in Ireland, so I kissed the Blarney Stone and know how to talk. That's the important thing. So if I'm too long, Catherine, interrupt me, say stop, wave and everything, and I will be trying to close down in the next hour. So that's the plan behind. I came here to make a PhD in Missouri at Washington University, ended up for a postdoc at MIT, stayed at MIT for a while, was a research scientist at MIT, started to teach at MIT, became a lecturer at Harvard, Boston University, Boston College, at different kind of universities. But broadly, I'm a broadly educated geologist, so I know a lot about rocks, and my field of expertise is geochronology, and as usually I have to make a nerdy joke, which is I'm dating rocks. They never complain. It's really great. So I apologize for everybody. It's a very nerdy joke what we have there. Thank you, Kathleen, for inviting me to actually speak to you. And I have to be honest, I'm a freshman in Jonathan Bayliss. So I actually never heard of Jonathan Bayliss before I got your email asking if I actually could talk to you about it. And so I started to look actually, I thought in preparation for this talk, to find actually the book and literature and try to prepare myself. And so I came across the book, the Gloucester books, what we actually have here. And so I got on Amazon, I have an Amazon Kindle, I got the Amazon Kindle out, and I know language scientists, my mother is a language scientist, they like to look for words. So I actually started to simply search for the word granite and sea. And so I recognized that actually in the book, a Gloucester book, what we have here, there are 83 mentioning of the sea. What we see there, and 79 mentionings of granite. My partner is interpreter at the DCR at Walden Pond, so I compared that to Walden, that famous book as a foreigner, which you have to read, and nobody actually get over the first chapter about the economy, what we actually see right there. I searched for granite, I found one mentioning of granite. I tried to find sea, I found 0 mentioning of sea in the Book of Walden. So it seemed to be that actually Jonathan Bayliss was enticed in the beautiful things of granite and the sea. And so the title of your meeting is actually very fitting what we're actually seeing in there. And so I started to read a little bit in that book, and I started to read along that part. And I recognized a couple of quotes which I actually really liked in his book about granites. And he actually quoted right here in the Gloucester book, the Gloucesterman, on page 142, if you're interested in that. He said, they left the narrow ridge of granites between the great seaward pit and the Lyke-Hoon shorelines, 200 years before the rock was scratched in the circuitous high road around the upland heath of the interior had found its northern parts more or less 60 feet above every besieging sea, and it was 40 feet above the level of fresh water. And I think it's a very nice description that actually in that rock granite there is time involved to form the rock and to develop actually what we see today. This description was he was driving in Gloucester around and he was looking at the rocks in the surrounding. He actually described this beautiful rock, and he said it's 200 million years before it actually got scratched, and we actually have a road into that rock, what we actually seeing right there in there. And a little bit further down that page, he actually described very nicely right here that the distinctive rusty granite, but in both words of Liberty and Living Budding Rock of Cape Gloucester, was washed nearly naked, waste by the sea, it confronted. So there's not a lot of biology. We saw a couple of birds, but we heard this morning that it's farming here in Gloucester is really hard on a granite. Granite is actually a really, really hard rock. And the other thing what I like on his description, at first I thought he's an engineer, but I heard he's a very precise accountant. Is that correct? Or something in this direction? If I remember in his history, what we're actually seeing in there, he's very precise in a lot of things what we actually hear. And what he describes in both of these passages really beautifully is actually that a granite is not simply a granite, but that there are multiple things in a granite, different colors. We find these rusty colors of granite in here. We find these bluish colors, the whitish colors of granites. We all walked along these granite walls here in Gloucester, in Andrews. This is from Andrews Point. In Boston, we see all these beautiful granite lines. And there's actually, in every rock, there is a little bit difference, what we actually can see in these different parts, what we have right there. So today, with you, I actually would like to explore 4 fundamental questions and explore actually and figure out 4 different things. The first questions, which we all actually should have asked right from the get-go is, what the heck is actually a granite? It's so easy to talk about. We are standing in a kitchen and we see a kitchen counter and some people say it's a granite. As a geologist, a lot of times what the kitchen maker are calling a granite is actually not a granite, it's a quartzite or a different kind of rock, what we're actually seeing in there. Sometimes we have, maybe some of you have larvacite, it was very fashionable a couple of years ago, which is a bluish kind of rock, what we see in there, which is totally different than actually that whitish rock. It's totally different than the rock we saw this morning, which was not from this area, from Maine, which is that pinkish kind of rock. So there are different kind of things. So what is a granite is a good question we actually should ask. Then the next question I would like to explore is, what is the geology of Cape Ann area? It's a fair question. How is it about that we are actually standing on that beautiful rock, what we have there? How does Cape Ann fit into the geology of eastern United States? To get a little bit bigger, I'm an earth scientist, so I think in planetary terms what we're actually seeing in there. And then the last question is, how do we form the landscape we are seeing today? How do we actually get to the landscape we actually have today? So that is these 4 questions I would like to explore very quickly. So it's not an in-depth exploration, it's more or less to explore all these different points. It's 1 semester course in the university to actually figure that out. I'm trying to do that very quickly, that we're actually doing that. So a lot of times, please bear with me. I'm using sometimes terms and other things, what we're seeing in there. So the first question is, what is actually a rock? Because a granite is a rock in them. It's a fair question. We actually always ask our students, what is actually a rock? And it turns out the definition for me as a geologist is actually a rock is a naturally occurring solid aggregate of 1 or more minerals. I just grabbed this morning, right here, a granite from the walkway. We're going a little bit later for your birds, to see the birds right there. And that rock and that granite, we can see it's not a homogeneous mass, but we can see small little parts in that granite. There are black stuff in that, there's white stuff in that, there is pink stuff, what we actually saw in the different parts. Here I actually brought another rock with me. This is not from here, this is actually from South Africa, but it has really, really big minerals in it, what we're actually seeing right there. So we have a rock which is made up out of multiple minerals, what we actually see. And so you probably all heard about minerals. The definition for me as a mineral is not the same as the pharmacist who are giving you minerals. For me, a mineral is a crystal, what we actually see a lot of different parts. You can actually pass these around if you want to have a closer look on that. And then, for me, a mineral is defined as a naturally occurring substance that is solid, inorganic, representable as a chemical formula, usually abiogenic. This is way more complicated than you actually need to know. Fundamentally, it's a chemical compound which is bond together and creates some solid structure. A lot of you probably heard of a mineral right here. I brought a big one with me for classes in that. This mineral is called quartz. All right, so this is a beautiful crystal of quartz. It has a chemical formula. All quartz you actually see, all sand on the beach you actually have around, has a chemical formula which is SiO2, silicon dioxide. As a chemist, we actually call that silicon dioxide. It has a crystalline structure. That means the silicates are strongly bond together in a solid kind of structure. That's the reason why it's solid, what we actually have here. That's the reason if I'm actually throwing that on someone, it hurts if you see that. It's not bouncing back. In contrast to water, which has actually flexible bonds, it actually has some solid structure, what we see there. So it's a solid, it has a chemical formula. There are a couple of other words, abiogenic, which is not really true because our teeth are actually minerals. They're hydroxyapatite, that's the name of the mineral, what we actually see in there. They're produced by biology, but nevertheless, we are still having that definition in there. It has an ordered atomic structure. Chemistry always likes to go into the same places over and over and over. That means that actually rocks, which are made out of minerals, have a lot of chemical components, which are somehow playing a fundamental role in a lot of different things. And if minerals are bonding together, they are actually forming extremely strong bonds or extremely weak bonds, if you're thinking about that. And a granite is multiple minerals. It's made out of 3 dominant minerals: quartz, potassium feldspar, and plagioclase. They are bonding at really, really high temperature, gluing together and melting together, fusing together to a very, very strong rock, what we actually see in. But when we are now attacking that material, we are starting to leach out the chemistry. So all the chemistry which is in the granite, which is a lot of times are metals, are actually seeping into the water, which is attracting the different materials, what we actually see right now. So if you are swimming in the quarry, that discussion was this morning, if we should actually jump into the quarry, we shouldn't do it because there are a lot of heavy metals in that, which are carcinogenic, which are poisonous, and so if you're actually swimming in that, you're actually drinking water, goodbye. If I say that correctly. You said natural evolution, if I say that correctly. And so this is a mineral, and so these minerals, here is another mineral which is actually beautiful. I brought it in because it's really nice and I like to show it around. It's a feldspar too, what we're seeing in there. They are forming rocks. So this is a rock. The blue lines you're actually seeing on here and the black lines are minerals, and there are a lot of smaller minerals in this rock as well. The blue mineral is called kyanite. The black mineral there is called staurolite. What is it? All right. So if you're starting to think about that, rocks, there are different kind of rocks. We probably all learned at one point there are rocks. They're called metamorphic, sedimentary, and igneous rocks. So that rock which is going around is called a metamorphic rock. It's called a change rock, the chemistry change, what we're seeing in there. Sedimentary rock, you all probably heard it. We're taking a rock, breaking it down into smaller pieces, transporting it to different locations, deposit it and make a new rock, sandstone, and all these different kind of things are called sedimentary rock. And then there's igneous rock. Igneous, the term igneous comes from the Greek, and the Greek name for igneous is fire. So it is a fire rock. That means it's actually molten. We are talking about taking a granite, whatever we have, which is going around that granite, and then heating it up to really, really high temperatures. We need to actually go up to above 800, 900 degrees Celsius to actually melt the rock. a lot of times when you're an artist and you're actually making some molten rock sculpture or different components, you put a flux into that, which lowers the melting temperature of different parts, what we are seeing in there. That's what the flux is. But we have to go to really, really high temperatures to melt. We are talking about temperatures we human wouldn't like. It's outside, it's maybe 20 degrees and I'm sweaty. So the situation is simply, we are seeing that it's actually really, really hot. We're melting it up, and then we're cooling down that rock. Cooling it slowly or quickly down the rock, and then the chemical elements, dependent on when they actually like to combine and come together, they are starting to form minerals. And so there's a specific sequence, how the minerals are actually crystallized, all these different kind of things. And the temperature for granite is around 800 degrees, and the minerals which are forming at that temperatures are potassium feldspar, which is that salmon pink color in that, plagioclase, which is a white color mineral, and quartz. They are starting to form that. And because it's hot, if you take something and you melt it together, it's really, really strong, what we see. Everybody experienced that when you forgot to put the plastic pot out of the pan, and the stupid plastic pot melts into the pan. It's really hard to get actually a pot. So that means that actually that rock is extremely hard. It's a very, very strong rock, what we're actually seeing right there. And so that makes it very interesting as a building material. That's the reason why we like to use actually rock or granite as pebblestone, because the carriages are going over it and they don't destroy that rock. It actually survives the hard winter and all the hard banging and everything what we're actually seeing right there. And so the quarry here is there to actually utilize that strongness of that granite to actually develop in them. So that melt is coming in here. And dependent on how quickly specific material is crystallizing, we are seeing rocks which have large crystals in them, and we see rocks which have small crystals. I brought with me, for example, here, this is a basalt. You maybe have heard the term basalt, which is also a rock made out of multiple minerals. I can't recognize any of the minerals with my naked eye. I have to cut it and make a thin section out of that and figure out what kind of minerals are in that. This is actually from the ocean floor. This is one of the basalts from the ocean floor, which I'm holding right here in my hand. What we're seeing in there, it's black in color and different parts. That means it actually came up to the surface on the ocean floor and cooled very, very quickly. It didn't have time to actually grow. It's like a human being. We need time to grow. We need time to get bigger. We need time, I need to get smaller this time, but nevertheless, it's a fundamental idea that we are actually needing time to grow. And if we have time to grow, we are making big minerals. And you're seeing big minerals going around, whereas in this basalt, we actually can't see that difference. That means granite is forming right here underneath the Earth's crust. This, what we are actually standing right on here, has a pressure. We can calculate the pressure from our granite of around 4 kilobars, which is around 10 kilometers depth. So you have to imagine that this granite we are standing on at one point was around 10 kilometers below the surface. And there it was isolated and had time to crystallize and build the big minerals, the feldspar, all that different parts, what we're seeing in them. In contrast, the basalt, which is coming up to the surface and flows onto the surface, is cooling really, really quickly. And so all the minerals are so minuscule, we cannot see that in the surface. Volcanoes, you don't see big minerals in a volcano. If you go to Mount St. Helens, you see there are no big minerals in the rhyolite you're actually seeing right there. And so on the top, we actually have rocks which are really, really small grained, and in the deep earth, we have rocks where we can see the different minerals. The rhyolite and the granite, these two rocks, have the same chemical composition. It's just the difference in speed, how we are actually cooling different materials in there. The basalt and the gabbro, you maybe have heard the term gabbro, I'm not sure. It's the same kind, not heard. It's fine, but it's the same fundamental idea, it's the same chemical composition. It's just a different time speed, what we actually see. All right, and so now we have granite, and we can actually now go and find geographically where specific granites and specific rocks are. We can go to Massachusetts. This is a geologic bedrock map. You can actually download it for free. It's always nice to point out that the USGS, all the material from the USGS is actually free. You can download that. That geologic map you can download, and you can actually look at the distribution of the different rocks. Each of the colors represents some sort of a rock type, what we actually see in there. Just looking at Massachusetts, we can see actually there is some sort of change if you're looking at this part of Massachusetts compared to the western part of Massachusetts. Here we can see these lines. There seem to be everything sort of aligned in one direction, whereas here, sort of a rotation, what we're actually seeing in that. And then I would like to point out here is Cape Cod. All right? Anybody been to Cape Cod? Yes? All right, everybody has been to Cape Cod. How long did you wait on the bridge? 5 hours, 6 hours? All right, nevertheless, Cape Cod, I would like to point out that hook shape at Cape Cod. It's actually a glacial deposit, what we're seeing at Cape Cod. Whereas here we actually have real rocks on that side. We have the Berkshires right here in the back part of Massachusetts, and we are right now here. That is actually where Halibut State Park is, right at this point, which is slightly rotated compared to what we actually see in there, but nevertheless there's still some sort of striation, what we actually can observe in the geologic map, what we're seeing in here. So this is now a close-up of a geologic map of here, the Exeter region in that. I just cut out all the information, as you probably have. I don't know if you ever had a map where the map was that big. The sheet was 5 by 10 feet, and all the information and everything was in the surrounding. I just cut it out that we can actually have a little bit of focus in here. And each of the colors represent a specific rock type. Granite, gabbro, or different part. And pink is the color of granite. So if you're looking at that peninsula, what we're actually seeing right here, and that peninsula is mostly made out of granite. We are studying Gloucester is nothing else than granite. So the granite company couldn't be anywhere else in Massachusetts. Because there's so much granite here, the mining, the quarry is so much in the surrounding in here. Just to point for your orientation, Halibut State Park up here, Pigeon Cove, I think you went there yesterday, if I see that correctly. Pigeon Cove is right here. Rockport is here, Gloucester is right here, what we're actually seeing in there. That's the distribution, what we're seeing in different parts. And there's so many quarries up here, because everything is granite. Everything is granite, and everybody wanted to have the money from the pebblestone and from the rocks, because we are mining granite, and that's prosperous. We like to have that billion company, what we see there. Still today, we're going for mining companies, oil companies. They are the biggest companies in the United States, what we're seeing in there, because we all want to have oil. We all want to have plastic. We all want to have the different parts, what we are seeing in there. And so they prosper from what we actually see in these different parts. And I think these are just part of it, but there were 42 different quarries in the area. 42 different quarries in the area. A lot of you, I heard this morning, went actually out and learned swimming in these quarries, what we actually see there. Today we actually know. The other thing which is also very interesting, sorry, I'm running. Interesting, granite is full of radon. And so that's the reason why Gloucester, you don't really have basements or enclosed environments. You actually have to have air ventilation into the different parts because of the radon, what we're actually seeing in there. All right, I'm in quick what we're actually seeing in there. Here is again Halibut State Park. We can actually find here in the quarry different magmas. Different kind of magmas came together. We can find white magma, dark magma. We can find something what we call enclaves. We will look at an enclave. Unfortunately, a lot of that information is actually down at the coast. We are not going all the way down to the coastline because it's a little bit too far, and we are running out of time, if I'm seeing that correctly. All right, so we scientists, we like to do different kind of things. We like to do thin sections. We realize it's a calc-alkaline composition. We can date different materials, which is my area of expertise. I'm separating a mineral which is called zircon. Some of you know it as fake diamond. Zirconium, what we're actually seeing right there. Zircon contains uranium and lead, so I'm able to actually use that for radiometric dating. It turns out the granite, what we actually have here, is 425 million years old. What we're seeing in there, we can do geochemistry. Again, it's that calc-alkaline chemistry, what we're seeing in there. Calc-alkaline chemistry means it is related to something what we call in geology subduction zone. So it is a subduction zone granite. The subduction zone is we have tectonic plates in our surrounding where we're actually banging together different kind of plates. You have to imagine the Earth is sort of a pea soup or beans, and we have tons of crackers, and these crackers are plates which are floating around. Sometimes they bang together, sometimes they move apart, sometimes they slide side by side, all these different things. Subduction zone is where they actually bang together, where one plate is going underneath. That creates friction, that friction creates heat, that heat creates melt, that melt comes up to the surface, which creates a magma chamber to create a granite, which creates on the surface a volcano. Today, we have that on the west coast of the United States. Our volcano from this granite is in Salem. You just have to go down to Salem. You find actually the volcanic material, what we're actually looking in that. So here is, again, Cape Ann. We can actually take that and actually extend that to the entire east coast of the United States. You can see all the pink colors. We can find the same type of granite, the same age of the granite, all around the east coast of the United States. And so we are sitting on a subduction zone 400 million years ago, what we actually see right there. So 400 million years ago, this was how Massachusetts looked like. Like today, the Rocky Mountains. And now we have mountains. Rain starts to come in, drop by drop. We are breaking down that rock and creating one grain after the other, sedimentary rock, which is moving out into the different parts, what we're actually seeing in there. We even find now, actually this is at Andrews Pond, we find dikes which are younger, 200 to 50 million years old. This one is actually a 200 million year old dike. That was a time when the Atlantic started to open. So we can find evidence around here where we can actually see that the crust started to break apart and move apart again to create the Atlantic Ocean in that. And so now we have the big Atlantic, but we can find that around 150 million years ago, we started to create actually the ocean, what we are seeing in that. I would like to point out, I pointed out Cape Cod, that hook-like shape. If we're looking at this map, we actually can find the same hook-like shape right here. And that's an indication of a glacier for us. So we have a carving of a glacier. This is a glacier. If you think about it, that glacier moves forward. It's like a bulldozer moving stuff in front of me and that. And then it retreats. It simply melts. The ice melts and leaves the rocks behind. And that's the shape we are actually seeing right there. It's something what we call an end moraine in different parts. And we actually experience that here in New England. Sorry, I'm going way over my time. Your fault. We experience this at around 18,000 years. We have glacier here. We had a mile, even more, up to 10 kilometers of ice above us. Imagine, we are looking up here 10 kilometers, just ice, scraping and taking different materials out, what we're seeing in that. The extension was going all the way down to New York. If you actually go to Central Park, in the middle of Central Park is the end moraine of what we see in that. Of course, the Wall Street is on the other side of the glacier, and all the poor come not starting to social war, what we're actually seeing right here. Worldwide, we actually had a glaciation, what we're actually seeing all around, what we actually have here. Glacier at that time, imagine mountains. This is actually 10,000 feet tall mountains just peeking out of the glacier, what we're actually seeing right there on these different parts in that. I found it interesting because the glaciers also controlled and dried out the walkway between Alaska and Russia. And so the Clover people came over from Russia to Alaska and traveled along the glacier, the Laurentian ice shield, all the way to Boston. We actually can find evidence at that specific time in the Boston Harbor Islands, where actually the Clover people were hunter and gatherers because it was dry, what we actually see. If you're looking at that material, because all the water was frozen into glaciers, and less water was in the ocean. Oh, I'm in trouble. right here. People were hunting and gathering, what we are seeing right there, and that. And we can see actually in the Boston Harbor Islands a change in culture from hunter and gathering to fishing communities, what we actually see right there, because the glacier started to melt and move into the different parts. And then, of course, the humans have the last word in developing this landscape. Humans are changing the surface more than any nature did during the 4.67 billion years of Earth's history. And with that, I'm stopped.